Okay, not bad. Let's do one more example. How about the rotational inertia of a rod when rotated about its center? So, picture something like a meter stick, and the axis is going right through the 50 centimeter mark, and then we imagine trying to spin it like that. All right, if we say this whole thing has a length of L, and then I suppose if this is the origin, this is positive L over 2, and this is negative L over 2. So our starting point is always the same. It's the definition of rotational inertia, the integral of r squared dm. And take my advice, picture what the dm looks like. Dm is just a tiny little bit. Maybe we cut a meter stick up into a bunch of 1 millimeter slices. All right, we'd have a whole lot of them in a meter stick then, right? So dm is a very small fraction of the overall mass, and in fact it's so small that it takes up a width of dx. Okay, I'm going to assume that the meter stick is all made of one type of wood. It's not like the wood at this end is more or less dense than the wood over at this end. So if I were to picture any one of these little things that I call dm, they all have the same density as the entire rod itself. So if I find the density, and normally we think of density as kilograms per cubic meter, but that's what we call volume density. There's also such thing known as linear density, and linear density would be the amount of kilograms per meter, or kilograms per centimeter, or kilograms per millimeter, whatever you want to call it. For now, we'll say kilograms per meter. So how do I find the linear density of this meter stick? There's a couple ways I could do it. I could take the mass of the whole stick and divide it by its entire length, or I could take just the fractional mass of my little piece I call dm and divide it by the length taken up by that little piece, which is our dx value. Well, it's of uniform density, so those should give me the same value. In other words, if I cross multiply, dm is equal to m over L times dx. So that's going to allow me to make a substitution into the formula. So the rotational inertia of the rod about its center is equal to the integral of r squared times m over L dx. Wait a minute, what's another way of thinking of r? So r is just the distance between any value of dm and the axis of rotation. So the value of r for that piece would be labeled this way. If I want to find the value of r for this piece, there it is. How about this dm? That's its value of r. So r is a variable. R changes for every particular dm that you picture. Now wait a minute. This r just looks like it's the same thing as what I would call the value of x, right? It's the position of each dm along some x-axis. So let's write it as such and say I is equal to the integral of x squared times m over L dx. So this is step number 1. Here's step number 2 of our derivation, step number 3. So on to step number 4. We take out of the integral sign whatever we can, and we're left with the integral of x squared dx, and let's put our limits of integration into the formula. The very first dm we have to account for sits over here at a value of x equals negative L over 2. And then we've got to add to it that piece's rotational inertia, and then that piece, and that piece, and that piece, and that piece, and on and on. We'll get to one piece that doesn't contribute at all to the rotational inertia because it has no value of r. And then finally we work our way up to this last piece. So the lower limit is at x equals negative L over 2. And the upper limit is at x equals positive L over 2. I guess if we wanted to, we could just double it. Say it's 2 times m over L times the integral from 0 to L over 2 x squared dx. Okay, and then what does this calculate out to? Right, isn't it 1/3 x cubed? And we're evaluating that from 0 to L over 2. So in our next step, we get the rotational inertia is 2m over L times 1/3 L over 2 squared, which gives us 2/3 m over L times L squared over 4. Oh, I'm sorry. Squared. Cubed. Cubed. So this is cubed. And this is 8. Got that? 1/3 x cubed. Our lower limit just gives us a value of 0. So our upper limit of L over 2 cubed, L cubed, and 2 cubed is 8. I think we've got this right. I think we get 2 24ths. And then we have an L cubed in the numerator and an L in the denominator. So we have 2 24ths ml squared. Or in other words, 1/12 ml squared. Is that right? Scroll up. Well, this is a bit messy now, but this does say 1/12 ml squared. Let's double check that. Let's insert a photo. Oh, this isn't the one I wanted to look at. That's the rod about its central axis going this way. Here's the one we're looking at. Yeah. The rod about an axis this way, and it is 1/12 ml squared. Yay.